Welcome to Mr. Sweeney's AP Physics C class. Today we're going to be talking about kinetic energy, potential energy, and power. And we're going to start off today talking about kinetic energy. Kinetic energy is the energy of motion. So there's some energy component associated with when things move. This idea is considered, or what we term as kinetic energy. The faster an object is moving, the more kinetic energy that object has. Conversely, the larger the mass of a moving object for a particular velocity, the more kinetic energy it has. So kinetic energy itself depends on both mass and velocity. If we look at how to calculate kinetic energy, calculating kinetic energy can be done with the following equation. Kinetic energy equals 1/2 mass times velocity squared, where the capital K is the term or is the symbol for kinetic energy that is measured in joules. The mass of the object is measured in kilograms, and the velocity of the object is measured in meters per second. If we look at the relationship between kinetic energy and velocity, we can see that the kinetic energy goes up exponentially as velocity increases. This we could also see in the equation because K is proportional to the square of velocity. Now the next portion of your notes, we have 3 examples on kinetic energy. At the end of this note packet, you'll see the answers for those 3 problems. So please try those and check your answers when you get to the end of this notes. Moving on to our next section, we're going to talk about power. Power is the rate at which work or energy is expended. So either you're doing work that expends a certain amount of power, or that takes a certain amount of power to do an amount of work in a particular amount of time, or you could look at it in the sense that as energy is expended to do work, you could also calculate the power done if you look at either energy expended or work done. Mathematically, we can figure out what power is by dividing work by time, and power is a scalar quantity. There's a few different ways that we can calculate power, most of them having to do with the fact that work can be represented by different terms. We could just do work divided by time, or change in energy divided by time. That would be the first idea. The second equation for calculating power would be force times distance divided by time. Force times distance is work. But we can look at this as 2 separate items if we're considering, say, how far something with a power rating can actually be moved. We would use force distance divided by time. And finally, if we want to know how much power is being expended, you can look at a force that's being applied to something by the velocity it's moving at. So if you're applying a force to something with a velocity, force times velocity will determine what the power actually is being applied there. For these terms, capital P is power, the capital W can be work or could represent energy, F is force, and D is distance or displacement. V would be the average velocity, and of course T represents time. If we're looking at the units of power, the units of power are the watts. We use the symbol capital W to represent the unit watt, but with respect to that, don't confuse that with the capital W that's used for work. Sometimes it can be confusing. I highly suggest, and I oftentimes do this, that when you're representing the units of watts, you just write out watts instead of the capital W, just to avoid any confusion with the symbol W for work. And a watt is equal to 1 joule per second. If we're looking at the fundamental units that make up a watt is a joule per second. A joule is a kilogram meter squared per second squared. So if we look at it and we divide a kilogram meter squared per second squared, we end up getting a kilogram meter squared per second cubed. And that is the fundamental units for the unit that the derived unit that we refer to as a watt. Looking at this from a calculus point of view, power is work divided by time, but if you look at instantaneous power instead of average power, we could shrink the power and time to as a limit approaching 0 for the time frame, At that point, the average work approaches the instantaneous work. So power can be looked at any instance as the derivative of work with respect to time, but we could also look at it as the derivative of energy with respect to time if the energy is being done to power the system. So this next section has three different example problems on power. Similar to the kinetic energy example, the key to these three problems is at the end of the notes. So I highly suggest you try these three problems, check your work at the end of the notes, make sure that you came up with those values. In the meantime, let's move on to talking about potential energy. A part of this has been covered in class, primarily the conservative forces parts of it. We're going to finish up this specifically, talk about springs in here. So if we look at potential energy is the energy associated with the position or arrangements of parts of a system. What this means is that you can rearrange your system either by stretching it or compressing it, by moving an object in a field. That's going to reconfigure its pieces, and during this reconfiguration, it is possible to store energy into the system. That stored energy is referred to as potential energy. We're going to look at specifically two types of potential energy. First one being gravitational potential energy, with the second one being elastic potential energy. So whenever we talk about potential energy, in order for energy to be stored by a system, the most common way that energy is stored is by storing it through the use of a conservative force. So I'm going to review what a conservative force is right now. A force is conservative if the work done by it doesn't depend on the path taken during the application of the force. An example of this would be if you are trying to find how much kinetic energy you have at the bottom of the slide. It doesn't matter how twisting and turning the slide is if you neglect friction. Once you get to the end, it's really your change in height which will determine your kinetic energy. It does not depend on the path of the slide itself. The second way to recognize a conservative force is that if you move along a closed path, what a closed path means is that you come back to your initial position. So if you leave a position, you come back to that position. If the work done to move along the closed path is zero, that force must be conservative. The final way to recognize a conservative force is that if you do work on a system through a force, the energy gained by the system must be equal to the work done. What this last point really is referring to is the fact that there's no friction in that system. If there's friction in the system, some of the work done by a force will go into the kinetic or into entropy, increasing the heat of the system. That work itself is no longer useful. Even though we can account for it, it doesn't really add any energy to be stored in the system because that energy is no longer useful. So if there's no friction involved, then the work that's being done must go into the energy of the system. That means that the force is conservative. So let's start talking about a couple different examples of potential energy. We'll start with gravitational potential energy. That's the energy due to an elevation of an object. Very similar to last year, we used the symbol U to represent potential energy. And potential energy is calculated by determining your mass times gravity times height. Note that your mass times gravity is your force of gravity, and height would be your displacement. So your potential energy equation really is just referring to the force times displacement, mg being the force, h being the displacement. The other type we're going to look at is elastic potential energy. Elastic potential energy is the energy due to the stretching of an elastic material. The most common example of this is, of course, a spring, which you could also look at like a bungee cord, a rubber band, anything that could be compressed that kind of bounces back to its original material, even something like a bouncy ball, that can be considered an elastic material. In this scenario, the potential energy stored in the system is going to be equal to 1/2 k delta x squared, k being the spring constant and delta x being the displacement of the spring from its equilibrium position. So how much has it been elongated, how much has it been compressed, whatever the difference in its length compared to its original length is our change in position. So that's our delta x here. And finally, we're going to talk about Hooke's law. Hooke's law also refers to elastic material and elastic potential energy. It relates how much force is being placed on some elastic material compared to its elongation. Again, here K is the spring constant. It's measuring the stiffness of the spring. Delta X being how much the spring has elongated or compressed. Note that the force is going to be equal to the negative K delta X. That negative is referring to as you elongate a spring, the direction in which the elongation is occurring is opposite the way that the force of the object is placing at you. So when you elongate a spring, the spring is pulling to try to contract itself back together. If you were to compress a spring, the spring would be pushing out in the direction that you're compressing it. So the direction that we have in this delta X term cannot share sign with the force term because the force is always acting opposite that direction. Looking at Hooke's law, just a couple things specifically about it. First, the spring constant K is a property of the spring that does not depend on the scenario, just on the physical configuration of the spring itself. It's really a measure of the stiffness of the spring. The higher the spring constant K, the stiffer the spring is. And if you wanted to determine the spring constant of a particular spring, the easiest way to do that is to graph the spring, elongation, and forces. And if you graph force as a function of displacement, you will end up finding, for an ideal spring, a linear line with the slope of that line being the spring constant of the spring itself. So these ones, or these examples, these notes cover kinetic energy, power, and potential energy. Of the 6 examples that you had, I'll leave this one up here. We had the 3 examples from kinetic energy, and there's the answers to those, as well as the 3 examples from potential energy and the answers to those. Please try these examples to make sure that you understand this material. This is the more rudimentary perspective of it. And that is it. Thank you.